Good morning, everyone. It's Charlie Jordan again, here bringing you another lesson for Algebra II Trig. Today, we're going to continue focusing on exponential and logarithmic functions, but we're going to be moving away from graphing and we're going to be focusing on equations. So, because we're moving on to essential concept number 2. So go ahead, without any further ado, let's begin. First, we need to start reviewing some properties. So our first property is log base b of 1 equals 0. Now remember, a log is asking, what can I raise my base to in order to equal what I'm taking the log of? And we know from Algebra 1 and our exponent rules that to equal 1, we need to raise any number, no matter what it is, to 0. So if you saw this in a problem, you would see maybe log base 13 of 1. Meaning, what can I raise 13 to in order to equal 1? That answer would be 0. Our second property is saying, if I have log base b of b, where my base and what I'm taking the log of match, then it's going to equal 1. So an example of what you would see in a problem would be something like maybe log base 4 of 4. What do I need to raise 4 to in order to equal 4? 1, right? I just need to raise it to the first power. So that right there could simplify to 1. Our third property is going to be log base b of b to the x. What do I need to raise my b to, my base b, to make it equal b to the x? X. Here's what it would look like in a problem. Log base 2 of 2 to the x. What do I need to raise this 2 to in order to equal 2 to the x? I need to raise it to x. There's our answer. And finally, b being raised to log base b of x equals x. What that's going to be, whenever our base of our exponential function and the base of our log match, we know that it's going to equal what we were taking the log of. So that would look like this. 10 raised to log of x. What's the base right there? We don't see a base. Right, we understand that it's 10. So we know that that's going to equal x. So those are some basic properties that simplify to more of a single answer. So let's look at some more properties. These are going to help us condense problems down. Let's go back to some more exponent rules. X squared times x cubed. What would that simplify to? X to the 5th, right? But how did you get x to the 5th? What did you do? You added 2 and 3 together. So we know that multiplying with exponents translated to adding the two exponents together. So with logs, if we're taking the log of two things that are multiplying, that can translate to us adding those two. All right, so if we were taking log of a times b, that would translate to log of a plus log of b. We could also go the other way, which is why I have an arrow here going both ways. We could go from left to right, or we could take the addition and change it to the multiplication. If I gave you x to the 5th divided by x squared, and I asked you to simplify that, what would it simplify to? X cubed, right? But how did you get x cubed? What did you do? You said 5 minus 2, right? Okay, so we knew that if we were dividing exponents, that translated to subtraction. Same thing with logarithms. If we're saying log of whatever our base is, where a is divided by b, we can say log of a minus log of b. Hence, look at this, okay, the whole time my bases are never changing. My base is remaining the same. In this case, we understand that the base is 10, but your base can be anything. Our third exponent rule, x squared raised to the 3rd power, x squared cubed. What would that simplify to? X to the 6th. There we go. X to the 6th. But what did you do to get 6? You multiplied, right? So whenever we saw something being raised to a power, that translated to multiplication. When we're taking the log of something and it's being raised to a power, we can translate that to multiplying what our power was times log of that same base base is not a good word, but the same number right there. And last but not least, we need to remember that we cannot take the log of a negative or a 0. We learned that last week. We established that idea whenever we graphed the logarithms, and we determined that we couldn't ever take the log of something where we would be able to make it 0. We can't raise any number to a power to equal 0. And we looked at that with negatives as well. So we established that understanding last week. So let's go ahead and let's move into exponential equations. So our first step is going to be to isolate the base and the exponent. Because think about a regular equation. If I gave you 2x plus 3 equals 0, and I asked you to solve that equation, what would I mean whenever I asked you to solve it? I would want you to get x by itself, right? Okay, here we need to isolate the base and the exponent because where is our variable located? Our variable is located in the exponent. That's what makes the problem an exponential function, right? We talked about that in week 1. Once we isolate the base and the exponent, we're going to convert to a logarithmic form, okay? And to do that, you're going to hear me tell you to take the natural log of both sides or ln both sides. I'll say the thing. We're going to learn what that means shortly. And then we're going to solve the equation. So let's begin. We have 5 times e to the 2x plus 4 minus 8 equals 0. Now my goal is to eventually find out what x is. So step 1 is going to be to isolate my base and my exponent because I have to be able to get to x. So how are we going to do that in this problem? If this problem said 5x minus 8, if it was an exponential, if it was going all the way back to middle school, 5x minus 8 equals 0, what would your first step be? To add 8 to both sides. That's exactly what we're going to do here. All of those rules that we learned way back when, beginning probably maybe in 7th grade, those still apply. What you do to one side, you still do to the other. Solving equations is still the same idea, even when there's an exponential function there. Once again, I still need to get e to the 2x plus 4 by itself. So how am I going to do that? I'm going to divide both sides by 5. So now I have e to the 2x plus 4 equals 8 over 5. Is my exponent and base isolated? Yes, it is. So our next step is to change this problem to a logarithmic function. And to do that, I'm going to show you what it means to take the natural log of both sides. Okay, so this is what it looks like. But why is this allowed? We can do this because what we did to one side, we did to the other, right? Just like up here, when we added 8 to our left-hand side, we also had to add 8 to our right-hand side. In 3rd quarter, when we were solving quadratic equations, we were solving by quadratic formula, factoring square roots, right? If we square rooted one side, we had to square root the other side, right? Okay, logarithms are a function just like square roots are a function. So we can take the log of one side and take the log of another. You could also use log instead of natural log. Honestly, like using natural log because it's shorter to write. But either log or natural log because both are buttons on your calculator, which means that you can evaluate them. Okay, so now let's talk about this. We still need to get up here into this exponent, right? So we can use our properties of logs. What property did we talk about in the very beginning of the lesson that would allow us to get to this exponent? It was property number 3, right, on that second slide. So it taught us that we could take our exponent and we can change this to multiplication. So we can then take this and move it to the front. And what that's going to look like is right here. 2x plus 4 times the natural log of e equals 8 over 5. Now we need to keep simplifying. Let me ask you something. Who remembers what the natural log, what it is? It's log base e, right? Okay, so we can rewrite that. Log base e of e. Now let's use another property. What did we learn about was when our base and what we're taking the log of match, what can we simplify that to? We can simplify it to 1. How beautiful is that? okay? We know that 1 is not going to change my 2x plus 4, so let's rewrite that to now 2x plus 4 equals natural log of 8 over 5. I'm wanting to get x by itself. That is my goal. Now I'm back to our basic two-step equation. What am I going to do next? Subtract 4 from both sides. And then divide by 2. Now, if you're in my classroom, I'm going to preach to you at some point about round-off error. Guys, you could have started typing ln of 8 over 5 in your calculator a long time ago. But the more you touch your calculator, the more you're having to round, which makes your answer more inaccurate. So you're going to wait, and you're going to put all of this in your calculator at one time, okay? And it's going to give you, it's going to be an estimation or approximation, but it's going to be as close as possible. And that answer is going to be negative 1.76. This step here is our exact answer, and this step here is our approximated answer, okay? So, but if we would have started typing ln of 8 over 5 way back a few steps ago, our answer would have been a little bit different. But this is going to be as close to an accurate answer as we can get other than the step before. So let's go back and let's talk about the college scenario that we talked about on week 1. You are a junior in high school, you've picked your college, and you've learned that they're going to have a 5% increase over the next 5 years. And the base tuition this year was $4,000. We talked about that next year you would have to pay $4,200, and we figured that out. We figured out that we were having to pay 105% the next year, every year for 5 years. We would pay 105% of the year before. Well, we had to do that step 5 times, right? And we talked about how there could be human error and how it's kind of tedious. Well, today we're going to write a function that's going to make our problem so much quicker and so much easier. Standard form, y equals a times b to the x. Remember, a was our initial value and b was our growth factor. We talked about that in week 1. So, what is our initial value in this problem? $4,000. That's what the tuition was, right? Okay. We also need to know our growth factor. What percentage of tuition are you paying each subsequent year? That was 105%, right? But we know we can't write 105% in an equation. We have to write that in decimal form, so we're going to write that as 1.05. So we know our initial value, we know our growth factor, and we can write a function. Y equals A. A is our initial value. So y equals 4,000 times b to the x. B is our growth factor. What was our growth factor? 1.05. Lastly, x. What is x? X was our number of years, so maybe let's pick a more purposeful variable. Maybe let's pick t for time, and knowing that time is in years. It's important to know your units because 5 seconds and 5 years are 2 totally different things, right? Okay, so we need to know that 5 is years. So here's our function, y equals 4,000 times 1.05 raised to the t. They were wanting to know how much would tuition be your senior year of college, and we determined that your senior year would be the 5th year tuition increase. So we need to plug a 5 in for our t. Once again, we're going to put all of this in our calculator at one time in one step, and that's going to be $5,105.13. Guess what? That is the same answer that we found in week 1. However, we only had to touch our calculator one time instead of 5. How wonderful was that? Let's change this problem up a little bit. Instead of saying over the next 5 years, this committee has decided that they need tuition to be roughly around $6,000. So they want to know how long it's going to take to reach $6,000. So instead, we're looking for t this time. We don't know how many years. But we do know that in the end, they want it to equal $6,000. Remember, our first step to solve an exponential function is to isolate our exponent and our base. So how are we going to isolate 1.05? Divide both sides by 4,000, exactly. 6,000 divided by 4,000 is going to reduce to 3 halves. So 3 halves equals 1.05t, to the t, sorry. Okay, and then so our base and our exponent's isolated. So our next step was to convert this to a logarithmic function. We want to take the ln of both sides. Using our properties of logs, how can we get to this t? We can move it to the front, right? So we have ln of 3/2 equals t times ln of 1.05. Remember, our goal is to isolate our variable. We need to get t by itself. So how are we going to do that? We're going to divide both sides by ln of 1.05. Now, remember, we want to put all of this in our calculator at one time to avoid round-off error. So when you type all that in, it's going to equal 8.31 and some other numbers, but we rounded it to the hundredths place. But what does this answer mean? What does it tell us? They were asking how many years the tuition increase needed to be in place to equal approximately $6,000. So should we go with 8 years or should we go with 9 years? Well, the committee is very conscious of their students and their budget, so they don't want to overcharge their students. So they're going to go with 8 years. The tuition increase is going to be in place for 8 years. All right, logarithmic equations. We're going to combine our logarithms. Using our properties, we only want to see one log in our equation eventually. Then we're going to isolate that logarithm and we're going to convert it to an exponential. Remember last week how we spent so much time discussing converting? There was a reason for that. Then we're going to solve and we're going to check for extraneous solutions. But why do we need to check for extraneous solutions? Because remember, we cannot take the log of a 0 or a negative, so we're going to have to make sure that is not happening. So we have log of x equals 1 minus log of x minus 3. My first step was to combine my logarithms. I already have a 1 over here, so why don't we take this negative log of x minus 3 and move it over here with our log of x? How would we do that? The same way we would with any other equation, right? We're going to add it to both sides. So now we have log of x plus log of x minus 3 equals 1. Let's use our properties of logs, and we know that addition translates to what operation? Multiplication. So we can say log of x times x minus 3. Now, we have our log completely isolated. It's down to 1 log, so now we can convert. What was the base of this logarithm? 10, right? So I'm saying, what do I need to raise 10 to in order to equal x times x minus 3? Remember, 10 was already paired with this expression right here, so it can't be paired with it the second time. Our log already equaled 1, so our exponential function needs to equal something else. It can't equal 1 anymore. So that's 10 to the 1 equals x times x minus 3. Now, I don't like my x's on the right side. You may be fine with it, but remember, this is an equation. It's a balance. I can switch it as long as I don't change anything about it. So I'm just going to take that and I'm going to flip it around. Didn't change anything, just swap sides. All right, now I need to continue simplifying. So to do that, I'm going to distribute. X times x is x squared. X times negative 3 is negative 3x equals 10. What do you notice about this line right here? It's a quadratic equation, yes. How do we solve quadratic equations? We can graph. We can use the quadratic formula. This one really wouldn't be good for square root. Maybe we could solve by completing the square. But my personal favorite way is to factor. It may not be yours, but I promise it's the quickest in this scenario. So to factor, we must equal 0. So we need to subtract 10 from both sides. Now remember factoring. I'm trying to find two numbers that multiply to give me negative 10, but subtract to give me negative 3. So I know 10, I could say 1 times 10 or 5 times 2. 10 minus 1 is going to give me 9, so that's not going to work. 5 minus 2 will give me 3, but I want it to be a negative 3. So I need to say 2 minus 5, which lets me know that my 5 is negative once I factor. 5x minus 5, x plus 2. Knowing that we have to equal 0, we know one of these have to equal 0. So we're going to set them both to equal to 0. So we get x equals 5 and x equals negative 2. We found our solutions. But wait, we have to check for extraneous solutions, right? We can't take the log of a 0 or a negative. So let's start with 5. Log of 5 equals 1 minus log of 5 minus 3. We have some parentheses that we need to simplify. 5 minus 3 reduces to 2. I have log of 5 and log of 2. Do I see any zeros or any negatives? No. So 5 is a solution. We still have to check our other solution, negative 2. Log of negative 2 equals 1 minus log of negative 2 minus 3. I have some parentheses that I need to simplify. Negative 2 minus negative 3 simplifies to negative 5. Do I see any zeros that I'm taking the log of? No. Do I see any negatives I'm taking the log of? Yes. So negative 2 is not a solution. That lets us know that 5 is our only solution. But let's talk about this in a problem. Remember our skydiving problem last week? Yeah, this was the function that was used so that the skydivers knew exactly when to release their parachute at the right time. Remember, they need to release their parachute at 760 meters. Okay, so we have this problem right here. We're looking for what pressure does the altimeter need to read. So I'm looking for a height of 760. How am I going to solve this problem? I need to isolate my logarithm. How am I going to do that? Divide both sides by negative 8,005. Yes. So remember, I'm not touching my calculator yet though. So we're going to rewrite that as a fraction. Negative 760 divided by 8,005 equals ln of p divided by 101,300. Okay, my logarithm is isolated. So what do I need to do next? I need to convert. Remember, natural log is the same thing as log base e. So when we convert that, our base was e, so our base here is e. I know that this fraction right here does not look like an exponent, but I promise it is. The fraction was just so high, it's so tall, it doesn't look like it, but it is, okay? Now remember, our goal is still to isolate p. So how are we going to do that? Multiply both sides by 101,300. Yes. And remember, we're going to put all of this in our calculator at one time so that we can get the most accurate answer possible. We know this is our exact answer, but it still doesn't tell us what pressure their tool needs to read to display 760 meters, does it? But if we put all this in, we know that it's going to need to read 92,124.94 pascals. So that is when that is the pressure, when the altimeter reads that pressure, the skydiver will see 760 meters and he'll pull the parachute, right? Okay, so that was a lot of information in a very short amount of time. But guys, guess what? We're finished with exponential and logarithms. Next week, we're going to move on to trigonometric functions. Remember in geometry when you learned about sine, cosine, tangent? Maybe you learned SOHCAHTOA? We're going to bring that back. And next week, we're going to extend on that knowledge and we're going to learn about their sibling functions, secant, cosecant, and cotangent. So I hope that you come back next week and join me once again for another lesson. Remember that you are safer at home. Have a good day.